How to select transition model in *CCM+. The transition model that becomes available depends on your choice of RANS turbulence model. If you use the SST K omega model, both the turbulence suppression model and the gamma re theta transition models become available. With other turbulence models, turbulence suppression is the transition option available to select. After studying laminar modeling and transition flow modeling, let us shift our attention to turbulent flow modeling in *CCM+. What is turbulence modeling and how to conduct turbulent flow simulation in *CCM+ will be our focus here. So, first let us see what is a turbulence model. To obtain the Reynolds averaged Navier-Stokes or RANS equations, the Navier-Stokes equations for the instantaneous velocity and pressure fields are decomposed into a mean value and a fluctuating component. The averaging process may be thought of as time averaging for steady state situations and ensemble averaging for repeatable transient situations. The resulting equations for the mean quantities are essentially identical to the original equations, except that an additional term now appears in the momentum transport equation. This additional term is a tensor quantity known as the Reynolds stress tensor as shown. Reynolds stress tensor is modeled in terms of the mean flow quantities. This way, the equations are provided closure. Two basic approaches are used in *CCM+. Eddy viscosity models and Reynolds stress transport models. It is widely acknowledged that turbulence models are inexact representations of the physical phenomena being modeled, and no single turbulence model is the best for every flow simulation. Based on how the averaging takes place and how different treatments are applied to form turbulence equations. The overall turbulence modeling approach is divided in many types of turbulence models. Among these different types of models is the Eddy viscosity model. Eddy viscosity models use the concept of turbulent viscosity to model the Reynolds stress tensor as a function of mean flow quantities. The most common model is known as the Boussinesq approximation. The Eddy viscosity models in *CCM+ solve additional transport equations for scalar quantities that enable the turbulent viscosity to be derived. This gives rise to three different turbulence models: Spalart-Almaraz, K-Epsilon and K-omega models. Reynolds stress transport models, also known as second moment closure models, solve transport equations and are solved for each component of the Reynolds stress tensor. Let us discuss turbulence models in some more detail here. There are four major classes of turbulence models currently in *CCM+. Spalart-Almaraz models. These are a good choice for applications in which the boundary layers are largely attached and separation is mild if it occurs. Typical examples would be flow over a wing, fuselage, or other aerospace external flow applications. The Spalart-Almaraz models for RANS equations are not suited to flows that are dominated by free shear layers, flows where complex recirculation occurs, or natural convection. K-Epsilon models. These provide a good compromise between robustness, computational cost, and accuracy. They are generally well suited to industrial type applications that contain complex recirculation with or without heat transfer. K-omega models. These are similar to K-Epsilon models in that two transport equations are solved but differ in the choice of the second transported turbulence variable. These models have seen most application in the aerospace industry. Therefore, they are recommended as an alternative to the Spalart-Almaris models for similar types of applications. Reynolds stress transport models are the most complex and computationally expensive models offered in STAR-CCM+. They are recommended for situations in which the turbulence is strongly anisotropic, such as the swirling flow in a cyclone separator. Let us quickly review each turbulence model. First is the K-Epsilon turbulence model. A K-Epsilon turbulence model is a two-equation model in which transport equations are solved for the turbulent kinetic energy and its dissipation rate. It uses following approaches for resolving the viscous sublayer: low Reynolds number, two-layer. STAR-CCM+ has a choice of 7 different K-Epsilon turbulence models. Standard K-Epsilon, Standard two-layer K-Epsilon, Standard low Reynolds number, Realizable K-Epsilon, Realizable two-layer K-Epsilon, Abe Kondo Nagano low Reynolds number, V2F low Reynolds number. What does a wall treatment mean? In the K-Epsilon models, the wall treatment performs these functions: specifies the reference velocity to be used in the wall loss, computes a special value of turbulent production in the wall cell, computes a special value of turbulent dissipation in the wall cell. 4 wall treatments are available as appropriate to the specific K-Epsilon model. High Y plus wall treatment, low Y plus wall treatment, all Y plus wall treatment, two-layer all Y plus wall treatment. What is the high Y plus wall treatment? High wall treatment is essentially the classic wall function approach where wall shear stress, turbulent production, and turbulent dissipation are all derived from equilibrium turbulent boundary layer theory. What is the low Y plus wall treatment? Low wall treatment is consistent with low Reynolds number models. This wall treatment assumes that the viscous sublayer is resolved and thus wall loss are not needed. What is the all Y plus wall treatment? All wall treatment is a hybrid approach that seeks to recover the behaviors of the other two wall treatments in the limit of fine or coarse meshes. What is the two-layer all Y plus wall treatment? Two-layer all wall treatment is a formulation that is identical to the all Y plus wall treatment but contains a wall boundary condition for that is consistent with the two-layer formulation.